All right. Good evening. Welcome, everyone. I'm Sam. I'm gonna, I guess let Brandon go ahead and start, introducing or Brandon. It's up to you, really.
Yep,
You-
no problem. I can kick it off. So thanks everyone for coming. This should be a good talk today. We have one of our own organizers. Sam's going to present on big data cluster services managed in the cloud. I think it's going to be a really good talk. If you have any questions, feel free to drop them in the chat and we'll get to them or interrupt. I'm sure Sam wouldn't mind either one. And then we also are going to record this. So if you don't want to be recorded, just make sure you turn off your screen. But otherwise, hand it over to Sam to get started.
All right. Thanks, Brandon. I appreciate it. Yeah. Feel free to stop me at any point if you want to go ahead and ask a quick question or drop in the chat. It's fine by me. Well, welcome. Thanks for showing up tonight. This is Accelerate Big Data Analytics with Managed Cluster Services. Like Brandon said, I'm Sam. I'm a co-organizer with this data meetup in Richmond. And I work at Ippon Technologies as data engineer. It's a boutique consulting firm. We specialize in data, obviously, cloud, DevOps, full stack application development, across all cloud platforms. And I'm part of the data practice. So, we have a few things that we, deliver from there. So a bunch, basically starting data initiatives at companies for like pretty much any type of workload, big data, fast data, whatever is needed, scoping from pretty much start to finish the whole thing. We have a pretty robust client portfolio now. We're about a year old. We have, customers in the financial sector like Cap One, Complex, which is cybersecurity, and it's led by Peter Cho. So he presented here last March. Fantastic data engineer or data guy in general. I've learned a lot from him, and we're hiring too. So if you guys have any, friends or you want to look for a new data engineering job, hit me up. Let's talk. But yeah, a little about me. I got some hands-on experience with Azure and AWS across a few projects. Currently, I've been pretty deep into Cassandra, which is a NoSQL store, and a lot of AWS compute services and analytics. And small fun fact, my team won first place at the 2020 Virginia Governor's Datathon. It was a ton of fun. That was a really fun story. So, feel free to ask any questions about this stuff afterwards because I love to talk about them. But here's tonight's agenda. We'll start with a quick introduction about background, context of the problem, and managed cluster services, some architecture and design. So basically, how this works under the hood a little bit, and what good solution design looks like. And then I'll contrast it with similar services because this might sound like very familiar verbiage. You might see with other services that might do something similar. But I assure you, there are differences, and this place has its purpose. The service has a purpose, and lessons learned, of course, because there's a ton of things I could share there, and some Q&A at the end. I'm expecting this to be about 25, 30 minutes of talking, maybe 35 minutes, but hopefully things will be wrapped up by like 6:30, 6:40. So yeah, let's go ahead and jump into pretty much defining what's a cluster, big data cluster, high performance computing cluster, all these terms that you might have heard before. So some background on big data computing. Basically, in the beginning, pre-1994 was your mainframe era. That was like your supercomputer, just one single big computer. And then in 1994, the Beowulf project got popular and then open source by NASA, and Linux got popular as well. And so people started to buy commodity hardware and connect identical machines to the same network, and that's how they would run their workloads. They would distribute it to a bunch of machines like that. And for these, the price would vary for, maybe 5 to 6 figures for the hardware alone. And then 2000s to kind of the present is, what I call the GPU era. So hardware starts to get better and folks start using GPU clusters to accelerate specific types of problems. So this would be like machine learning training in our field. You might hear of GPUs, pretty expensive ones being used for gaming graphics, of course, mining Bitcoin and things like that. And then again, the hardware can vary from 5 to 6 figures as well for this one. And then from 2010s to present is when the cloud started introducing their new services, and infrastructure as a service, PaaS, which is platform as a service offerings, which basically allow firms to run big data applications without having to buy or manage hardware. So it's a pretty big step from, previously where, you had to buy and manage things, install stuff yourself, to just being able to click a button and go ahead and start to like just develop right away. And there's something to be said about using on-prem hardware still. Like I think cloud might be advertised as being like a solution that one size fits all sort of deal, but I know that Carmack still uses on-prem hardware. And if you look at the pricing between cloud GPU and on-prem GPU, the quick math will show that like it might save you money if you actually just buy the hardware on-prem for things like machine learning workloads and stuff. So the benefits of infrastructure as a service, though, are pretty much it's going to guide like where like managed platforms as a service really has its benefit. So the big thing is here, you don't need to buy or manage hardware anymore. The whole thing about waiting minutes and not months. So basically, like I said, you click a couple buttons and then you have some infrastructure or some compute power available. You don't have to wait for something to ship and then come in and then install and stuff. So for the most case, I would say that pay-as-you-go hardware beats financing software, and I'll explain the graph on the other side in a second. Additionally, you can scale without hardware limitations, and so the user still needs to manage like installing OS, middleware, and applications and stuff. And examples of these would be like Amazon EC2, Azure VMs, and Google's Cloud Engine or Compute Engine. And so these graphs on the side, the top graph is like pay as you go. So basically the blue line shows how much like compute resources you're using. The red line shows how much you're getting billed for. And you're basically getting billed proportionally as how much you use. But if you're on-prem, your bill stays the same since you finance hardware, but you may not be using your resources to 100% capacity, but you're still paying for that either way. And if you end up having a spike, so like at that 4 right there in the on-prem chart, then you can't scale further than what your hardware, than its limit. So you're going to lose out there and still be paying the same and not be able to scale unless you want to finance more hardware. And a natural progression of this one is a platform as a service. That logo is Elastic Beanstalk, which is like web app development, PaaS on Amazon. It's kind of hard to see from the logo, but basically this is a step up from infrastructure as a service, where now the cloud provider will manage the OS, the database, and development tools. It can be cheaper than infrastructure as a service in certain cases, but faster development time because the software comes pre-configured. The developer just needs to start like pushing code and testing that stuff out. But yeah, the user still needs to manage applications, data, etc. And this is an overview of pretty much what all the as a services, the main 3, infrastructure as a service, platform as a service, and software as a service, pretty much do, what they take care of, what the service provider manages, and then what you end up managing. And of course, on site, you manage all of this stuff. But yeah, these are the main 3. I see new as a service sort of paradigms pop up every single year, but I would say that most services on cloud platforms, Amazon, Azure, fall into one of these 3 categories. And on top of that, getting familiar with this sort of graph is pretty helpful if you're going for a cloud certification, because they usually ask about it at some point. A software as a service example would be like Microsoft Office 365. And so managed cluster services, it's a type of PaaS that lets you run big data workloads. So you can spin up clusters on demand. It uses things like EC2 or the basic compute VM that your cloud provider has underneath. It's got support for a lot of open source tools like Spark, Hadoop, and some examples for each cloud is AWS Elastic MapReduce, Azure has HDInsight, and then Google Cloud has Dataproc. Today we'll be focusing mostly on EMR, Amazon Elastic MapReduce, because that's what I'm familiar with. I have a lot of experience with it. I've used it on a couple projects, but all of these guys do pretty much the same thing. I mean, that they all have the core like function. So a lot of these things, the benefits and the function apply to all the cloud environments. So the core benefits of a managed cluster service is that starting out, you get the cost savings associated with a platform as a service to begin with. So you still don't have to worry about managing hardware, software, the ease of use for developers. Basically, I mean, like you hit the ground running. You don't have to worry about installing, configuring anything, which is super great. Pretty low, I would say low, like, curve or low knowledge curve or something like that. Um, so it's pretty low barrier to entry. You can hit the ground running and start developing right away. Of course, integration with other cloud services. Most of these services are pretty mature and they're well linked up with other cloud services inside of the same ecosystem. So EMR works really well with S3, Lambda, step functions, but pretty much any sort of orchestration or other data product that Amazon has to offer. So that helps out a lot when it comes to linking your application with other things. It's elastic, so you can basically scale up and down as you need, and it's flexible too. So basically, the nature of it is that like you can customize the environment to get any sort of software on there you want, and you can use it to solve a variety of problems. And a few use cases of managed cluster services, we'll go through one at a time. ETL pipelines, all of these guys support installing Spark, open source Spark, which lets you build like data pipelines. You can do pretty big data processing with Spark, relatively cheap with a lot of these services. Big data migration, basically taking a big cluster and distributing some sort of like transfer either from S3 to another data store or from S3 to another S3 account. And it uses the cluster and distributes the workload. So like each VM inside the cluster takes a little bit of that file stored in S3 and does the work like that. So that's a pretty big benefit. Interactive analytics, if you have a data science team and you guys are trying to take a look at like terabytes of data, you can quickly ingest that and start to view it in a Jupyter notebook and do some analysis on it with PySpark or any sort of Spark with Scala. So that, it's pretty quick to do that. And then machine learning training, they support TensorFlow and Spark's MLlib as well. So you can do machine learning training on these as well. And the biggest takeaway of these managed cluster services is that they can be versatile and used in a variety of different workloads. Of course, it comes with the benefit that cloud services are typically known for: scalable, elastic, flexible, managed by AWS and the other cloud providers. And I think that a good understanding of architecture principles will help any sort of data engineer support a variety of projects, whether it be an ETL pipeline team, whether you're migrating a big data set, or helping out a data science team. So I think that this could end up being a cornerstone for many workloads, and it's really helpful to keep in the toolbox. So if you understand like the architecture principles of a managed cluster services, along with some Spark knowledge or Hadoop, MapReduce, or any other of the popular frameworks that they support, it can make you pretty strong as a data engineer. Yeah, you can support a lot. So the architecture and design of these big data workloads and managed cluster services, this is what it looks like for AWS EMR. So basically, on the right, you have like a little visual of a handful, 5 VMs, and shows how they're all connected to each other on the same network. You got 4 core nodes and a single master node. And consider each of these as an EC2 instance underneath. The master node is responsible for coordinating applications among the cluster. So it runs as the driver component for Spark apps, and it works on like figuring out which parts of a workload should go to which core node. You can also get SSH access if you need to directly run things in the cluster, or if you need to say check some logs that get written out locally. And then the core nodes, these do the heavy lifting for the application, so the actual processing, and they also store data for the Hadoop distributed file system. So, which is a component that Amazon EMR is built on, where like their data store underneath is pretty much a Hadoop distributed file system, or HDFS for short. And they also support using S3 as a distributed file store, that's all the experience I've used. I don't use Hadoop that much. Amazon even recommends to use S3 over Hadoop when it comes to doing Spark workloads. But This is how like distributed computing actually speeds up your workloads. I wouldn't say speeds up. I mean, it's still running, the same speed. It's still computing at the same speed, but it's just doing it across multiple computers at the same time. So the work gets effectively distributed among the cluster. So an example of this would be Hadoop MapReduce. And Hadoop is, it's a little older. I think that most of these products, these managed cluster services, are taking the Hadoop verbiage out from their product page. They're showing off things like how it can speed up Spark workloads, Kafka workloads, but you can't really talk about a cluster service without talking about MapReduce or Hadoop. And the way that MapReduce works is that, so this little visual on the bottom, take that input data set and, basically say that we want to count the occurrence of each in this input data set. So you've got your input, your map phase, and then your reduce phase. And so the map phase, each line of the data set gets parsed out and all the occurrences of animals are extracted. And that's what you get in the output of the map phase. And the map, that output there is just, it's basically just a list of all the occurrences of each animal and a one associated with it. Now that we have all animals by each line, we want to count the number of occurrences across the whole data set. So that's when the reduce phase, everything gets shuffled around to, pretty much the same type of animal. And then they combine the results. And that's what you get from the output of the reduce step. Now, the only downside about MapReduce is that it only does one map and reduce function per job. So it needs to like read it from disk and then store it back to disk after each call, which is, it makes it a little slow, basically. And that's where Spark comes in, and it's basically, it can speed up your workloads quite a bit. They say that it goes up to 100 times faster than Hadoop, but basically it uses a directed acyclic graph to plan workloads. And the main advantages over Hadoop is that it caches the results of the data sets. So, between MapReduce jobs, it doesn't have to write to disk each time. And so that, being able to use that all in RAM helps out quite a bit. It's also got a rich API that allows for pretty complicated transformations that might require 2 or 3 MapReduce jobs. And so, yeah, I mean, with those sort of things in mind, it speeds up the workloads pretty significantly. I've never used MapReduce. I was born using Spark, and it is pretty fast. I couldn't imagine having to write, basically do MapReduce jobs and then write everything to disk and then read back in. So yeah, Spark makes things pretty fast. For example, I mean, the project I'm working on right now, I think with a relatively small cluster, like 25 nodes, we were able to process and do some pretty complicated transformations on a 2 terabyte data set in like 2 hours. So that was pretty cool. That was pretty cool. And here's a couple examples of open source software that EMR, Amazon EMR, and likely the other data products from Google and Azure support as well. This one only has Spark selected. We'll hop into the console in a second so I can show off some more things. But they do have support for customizing your compute environment. You can enable logging, which is super cool. I mean, basically get all the output of the Spark jobs, any Bootstrap job, setup and things like that. You have SSH connection, so you can go into the master node and manually, submit jobs. Bootstrap scripts to install custom software packages. And then Amazon offers custom AMIs to achieve anything that a Bootstrap script can do. And so, yeah, let me go ahead and show, let me go ahead and share, let's see. I'm gonna open up the AWS console and show off a cluster I spun up earlier. And I ran a job on so you guys can see what it looks like. It's sort of a deep dive. So I'm gonna stop sharing my screen so I can move something over. Okay. I got logged out of the console, so I have to redo this. Let's share my screen again. All right. Can you guys see the console?
Yep.
Cool.
Yes.
All right. We're opening up EMR. Here's my active cluster right now. I spun this up, right before we started this presentation. And basically, this is what you see at a glance. Go back. These are our lists of clusters that we've created previously. The only one that's running is the one I have right now for the example. And at a glance, you can see quite a bit of information on the summary page. You have some like network and hardware stuff right here. So this is like a two node cluster with one master node. Security and access don't really worry about. Some of the applications I've installed on here, Spark and Ganglia. Ganglia is for resource monitoring. I wanted to show that off, but I couldn't get it set up, but life is not perfect. So, but I did submit a Spark job so you could see what that looks like. And so it failed the first time, which is fine. I wasn't gonna restart this whole cluster. And then the second time I was able to run my job, no problem. It was a very simple script. I mean, just took a data set, added 5 to a column, and then wrote it back to S3. So, and the Spark code is pretty simple itself too. Can you guys see the Spark code?
Yep.
Yep.
It's a little more verbose than Python. You got to import quite a bit more. But I mean, when you set up your Spark environment, this is what the syntax looks like for reading in data. It's just spark.read.json, and then this is my S3 location. I did a count on the data, and then I wrote it back to S3 after adding 5 to a column called devices. And that's me writing it back right there. So only took 20 seconds to do that. I mean, it was a really tiny data set too. Something I whipped up in a couple minutes. But yeah, this is what it would look like from, when you're actually hands-on with the cluster. So let me go ahead and get back to my presentation. Stop this screen share.
Sam, you got a few questions in the chat.
Oh, cool. Let me check them out. I'm going to share my screen again and then check out the questions. Thanks, Roland. All right, I seem to have lost my presentation. Just give me one sec, guys. You know what? I know why. There we go. Okay. I was looking in Safari for my presentation. Or sorry, I was looking in Google Chrome for it. I needed to look in Safari. There we go. All right. Let's get this up. Okay. I'll answer questions now. Let me just pull them up. It's a cluster era from 1994 to 2000 instead of 2010, or overlap in 2 different time eras. Yeah, actually, the overlap was on purpose. The overlap was definitely on purpose because, let me go back over here real quick. Yeah, the overlap was on purpose. So let's see. I mean, main computing clusters are, they're still used even today. I just kind of said like 2010 is the cutoff because that's like, I mean, when GPU started to really pick up, and of course the cloud was introduced. So honestly, those last 3 bullets, the cluster era, GPU era, and cloud era, they're all used today. I would say definitely though that like, we're seeing mostly GPU and cloud right now. And then Roland asked, did you say you can interface with Jupyter notebooks in EMR? Yes, you can interface with Jupyter notebooks in EMR. I'm not going to bring back up the console because it took like a hot second to get that set up, and I want to keep rolling. But you can set up and build with EMR notebooks, which makes things super easy. And that's where the data science support comes in. That's how you could really help out a data science support team or just explore your data in general. So let's go ahead and move on to the next section. And then Roland, at the end, I can pop back open the console if we want to look at it. But yes, you can use notebooks and it's very easy to get set up. I mean, EMR installs everything for you, which is nice.
Cool. Okay. Or maybe just a reference at the end, point me in the right direction would be great.
Sounds good. Sounds good, man. All right. So the next section will be a contrast with similar services, because I think I may have said some things that sound very much like other services. So the three services I'm going to address are Databricks, ETL tools, and then batch services. So starting out with Databricks. So Databricks is a managed Spark service. Databricks is like a company that contributes and manages Apache Spark, and they have their enterprise version of the service. Most Apache, like most of the bigger Apache projects like Cassandra, Airflow, they all have companies associated with them that they usually offer an enterprise version of it. And this is what Spark has. But what Databricks provides is they manage the compute, so they can configure and like automate your whole like Spark environment. They offer workflow automation and data pipelines and an integrated workspace. So similar to a notebook, but that's what the enterprise Spark service is. And EMR or any sort of managed cluster service, it just runs Spark jobs. So you can install open source Spark and run them there. So I would say that, if you need an enterprise Spark service, definitely go with Databricks. All right. So ETL tools, they can have similar function to a managed cluster service. An example of this would be Amazon Glue, maybe Matillion, but ETL, they generally are easier to configure ETL jobs with. I would say that they're less flexible though. Managed cluster service jobs can do ETL, but that's not what that's not their only purpose. They can do a lot of other things too. But yeah, if you need something that's very complicated, or you need like custom bootstrap scripts or very niche software, maybe consider using a managed cluster service, unless the ETL program or ETL tool can handle it. And just for reference, Amazon Glue is an ETL service on Amazon Web Services, and it works on top of a Spark environment. So you're getting some similar function in that sense. And the last one are batch services. And batch services are really meant to run any sort of batch computing job at any scale. Azure and Amazon Web Services has their own batch. And in a sense, they may be able to do some ETL use cases, but it is definitely not a cluster service. It does not run Spark or Hadoop. And it's also not an environment for interactive analytics. So, they have their use cases, but the takeaway from this is that the decision to use a managed cluster service depends on your workload. So just knowing your workload and seeing whether it fits the need for a managed cluster service is probably the main key. All right, so the last section will be lessons learned. And there's a lot, I've learned a lot, but I tried to distill them down to a few major points. So let's see. Tuning can be difficult. I've always felt that I've struggled with tuning these jobs, because when you're talking about big workloads and, not necessarily being able to run a 2 terabyte job every single day, because those clusters can get expensive and sometimes takes long times for these jobs to run. Understanding the services you're using, so whether it's Spark or EMR, and understand how to get an idea of what the resources are doing under the hood. So getting a good idea of logging, resource monitoring, those are all very important things to do. Because if you don't understand what you're doing, you may end up just pulling a whole bunch of different levers and seeing what works. Next one.
Thanks.
Best practices early. Yeah, I think that one's pretty self-explanatory. Anytime you really hop into some sort of new service or framework, you need to get an understanding of what the best practices look like, because you don't want to end up building something for 3 weeks and then realize you're doing something that's anti-pattern. Because that's not a good way to start off, working on something and then start building on something, is to, be doing something it's not meant to be used for. Brandon and I joked about one time when I was using Spark and I was trying to solve a weird problem. We called it Spark abuse, or just, abuse in general of like a big data framework when you're using it the way it's not meant to be used. So assessing what parts of your workload really warrant a managed cluster service or a cluster in general, because not all parts of an ETL pipeline need to be run on a cluster. You may have a large part in the beginning or at the end that might warrant the power of a cluster, but that doesn't mean that the entire ETL pipeline needs to be run with a managed cluster service. Know your data. Oh, yeah. I think that this one is incredibly important too. So understanding the quirks of your data, understanding, the limitations of it, pretty much everything. I mean, and this could vary based on your environment. If you're moving from dev to QA to prod, you might have different, your data might look different at each environment. So you got to study it basically exhaustively so you understand all of its weird quirks and make sure that nothing's going to break your pipeline or business logic. There was this one time where I was looking at a pretty big data set and, all of it looked pretty normal on the surface. And then I dove pretty deep into it to look for very niche things. I was dealing with I think it was some emails or something like that. And I noticed there were some very long ones. And I realized that somehow 100-line SQL queries got into my data set somehow. Strange. I don't know how it happened, but those are things that you have to be aware of because it could break your code. And the last one, explore different options before committing to a solution. I think that there's a lot of ways to get a lot of problems done and solve a lot of things. And oftentimes there might be multiple tools that sound right, which is why I broke down the differences between a managed cluster service and other familiar products or services. Because it might seem like there's a bunch of ways to get something done, but the Python Zen quote is something like, there's the easiest, the right solution should be the simplest, and there's always one solution. So definitely explore your options before committing to it, though. And that pretty much wraps it up. Connect with me. I like to talk about this stuff. I like to tinker with data and play with new technologies or services. And once COVID ends, I'm going to go back out there, networking events, throw it down on the dance floor, all sorts of stuff. So if any of that sounds like things you'd like to do, connect with me. Let's be friends. And again, I always welcome some sort of philosophical debate, whether it's material I presented or thoughts on architecture paradigms or the future of data and stuff like that. I love talking about that stuff. And lastly, Ippon is hiring too. So if you guys are looking for a data engineering position, or if you're a solutions architect or data architect, yeah, let's chat because we are hiring. That wraps up my presentation. Any more questions?
Yeah, Sam, can you point me to the direction you talked about with the Jupyter Notebooks and EMR connecting?
Right. I'm going to stop the screen share right now. All right, let's do this properly this time. Okay. All right, can you see the cluster console again?
Okay.
All right, so here we are. This is pretty much the basic intro to the cluster console. So if you go to EMR on EC2 and under notebooks, that's where you create a notebook and give it whatever name you want. But basically, once this notebook is ready to go, which only takes a few seconds, we can open it up, and I believe it uses Jupyter Hub, but it's a pretty fully managed and configured PySpark or regular Spark environment. And so yeah, it's pretty great. So that's where
it runs jobs against the cluster through that mechanism you're saying?
Yep. So you create a notebook, and then you mount it on whatever cluster you have available. So I'd end up using this one, and then it would end up, just spinning up and running jobs, submitting jobs directly against that cluster.
Oh, cool.
Yeah. So it's very handy. That's why I'm saying that data science teams can get started very quickly with processing terabytes, petabytes of data, because you have your Jupyter notebook right there handy, and you have a cluster that spins up in 5 minutes.
Perfect. Yeah. Thanks for the pointers.
For sure. I saw another question in the chat. Let me pull it back up. Are there any pitfalls when working with various Python package managers when in EMR? So I've always used pip to install my package, to install packages. I don't know if you're talking about, Ram, are you referring to creating your own Python packages within EMR? Or
No,
just
so generally my use cases is that my data analysts and data scientists, they give me a environmental.yaml file, and then they expect it to be deployed wherever they're going to be running their production models. So if we're working in EMR, is there any pitfalls associated with working with Conda, for example, or pip and B?
Oh yeah, that's a good question. So I've never worked with Conda, any sort of like virtual environment inside of EMR. My assumption is that, like, you know, when I'm working on a cluster, I spin it up for one purpose and then I kill it basically once I'm done at the end of the day. So I don't really worry about like isolated environments. And so I've only worked with pip inside of there, and I install my packages using a Bootstrap script. So in Bootstrap Actions, I usually submit like a script that just does, you know, pip install pandas, pip install. Well, I usually don't use pandas for this, but pip install really whatever packages I need. But I would not say I've run into any pitfalls so far, though. The only thing is that, like, I mean, when you're running a PySpark workload with a package, it's a little tricky to specify. Like, you're using like external packages. Sometimes there's like a dependency zip that you need to make, but no, I haven't run into that.
Gotcha. Thanks, Sam.
Mhm.
I have a question. Is a good practice to use the task nodes, or you have to measure like what's going to be your compute requirements and
Yeah.
just use the master and the core nodes?
That's a good question. So I've never worked with core nodes myself. I know that they're used to help. Wait, do you mean core or task nodes?
Task nodes, task.
So I've never worked with task nodes myself. I don't really understand how they're advertised to help parallelism with your cluster and jobs. I've never like gotten a chance to measure like the parallelism or seen something that like doesn't do what the core nodes are there for. So I don't know, man. I wouldn't say it's like a best practice to use them or not. I guess it's there if you need extra parallelism. So I don't know if that means like extra threading per worker, or whether it just means extra sort of Spark executors to like just run more things in parallel at the same time. So yeah, I don't know. That's a good question.
Yeah, I had a use case. We were working with a Scala Spark application.
Mm-hmm.
And the core nodes, you cannot scale up and down the core nodes automatically. You just scale the task nodes to help the core nodes.
Mm.
With the things about, yeah, I've not seen that many people use that very often. You just rely on the core nodes and you just do the measures before deploying your EMR cluster.
Yeah. It is interesting. It is interesting. I gotta look more into that. I'm writing a white paper on this, by the way. So probably by like the end of the month, definitely before the quarter ends, me and my team are writing a white paper on EMR specifically. So we have a couple paragraphs about task nodes, but I have not had to use them on a project just yet. Fun little weekend project right there.
Cool. Yeah.
Cool. Any other questions? Oh, I see that Vijay asked, how do you measure parallelism to know whether your cluster is working optimally or needs tuning? Yeah, that's a good question. So in my opinion, you know, Spark default parameters work very well in most cases, as long as you're following Spark best practices. So like making sure your data doesn't have like significant skew in it. But the defaults generally parallelize everything optimally. A way you can tell if your Spark cluster or your Spark job needs some tuning is if you open up your Spark console and you see that like something's like running way slower than it should be. Occasionally, and actually, I'll see if I can pull this up. You can see how long exactly each sort of task took. Oh, I'm not gonna be able to do it. But yeah, you can see how long each task took. And if you see like one task running way slower than the rest, then that's a bad sign. You know, things aren't being split up as well, distributed, parallelized as well as they should. So that's pretty much it. And then, you know, you can also add extra parallelization if you want to. But like I said, you know, without scaling Spark either out or in, or yeah, really just out or up, without scaling it, the optimal like settings are pretty much the defaults. So that's my recommendation for that. It's pretty rare that you need to actually tune Spark's parallelism because they do a good job of picking the best sort of like ways to thread up your application and workload. I hope that answers the question.
Oh, yeah, sure. Thanks.
Cool. Any other questions, guys? All right. Doesn't look like it. Well, we'll break. I hope you guys have a good night. Thanks for coming.
Thanks for the presentation.
Yeah, for sure.
Yeah, thank you. Nice job.
Thanks, guys. All right.
Thanks, Sam.
I'll see you later.